Okay, welcome back to another lesson in AP Calculus. We're in Unit 7, which is all about the definite integral, the indefinite integral, and the process of integration. In this lesson, we'll be looking at a new kind of integration where we have to use an algebraic substitution. So when we're differentiating composite functions, we always had to use the chain rule. Can you remember that? When you took the derivative of something, you then have to multiply by the chain, the derivative of the inside. So an analogous process for integration is called u-substitution. Let's see how it works. Okay, so we're confronted with the integral of x squared plus 1 to the fifth times 2x dx. And if you look at this, I think you can kind of imagine what must have been, if this is a derivative, what must have been multiplying by the chain. And it's not that it's to the right or after it. It's just that it's related to the derivative of the inside. So typically, not always, it's not a perfect rule, but typically we're going to want to let u be the thing on the inside of the most complicated operation. So I have this big thing to the fifth, so I'm going to let u be this, x squared plus 1. Now, take the differential of each side. So the differential of u is du, and the differential of x squared plus 1 is 2x dx. Now, when we do u-substitution, we need to make sure that every x is replaced with something involving u, and every dx becomes something involving du. This one works out really nicely. I'm going to replace the x squared plus 1 to the fifth with u to the fifth. And 2x dx is simply du. Now that I have it in this formula, I can use my integration formulas. And you'll remember, our integration formulas are usually written in terms of u, and this is kind of why. So this is u to the sixth over 6 plus c. But I can't leave the answer that way. I need to replace the u with what u is, x squared plus 1 over 6 to the sixth plus c. Now, I don't have a lot of room here. Maybe if I slide this down, but let's just while we're learning this, let's double check. And it's always a good idea to check your work with taking the derivative. So if I take the derivative, I should be able to get this original thing back. Now, sometimes when we do integration, the derivative of it, you have to do a lot of algebra to make it look the same. But in this case, that's not the case. So if I was to take the derivative of this, I would have to bring down the 6, and the 6 over 6 would cancel. So I would just have x squared plus 1 to the fifth times the chain rule, which is 2x. And if I'm taking a differential, I would have a dx, just like the original. So that's how that works. Okay, let's do another one. Okay, can you picture what I would let my u be here? I'm going to let it be this thing inside to the fourth power, the 2x cubed plus 5. Let's take a differential. Du is equal to 6x squared dx. Okay, well, in this case, it doesn't really work out perfectly. It's okay that the x squared and the dx are far away. That's not a problem because of the commutative property of multiplication. What is the issue is I've got this pesky little 6. So the way I handle this, there's a couple different things you could do, but the way I do it is I say, okay, I need x squared dx, so I'm going to solve for x squared dx. So I'll simply divide both sides by 6. And I usually write it with a fraction. 1/6 du equals x squared dx. Now I can replace everything. And the 2x cubed plus 5 to the fourth becomes u to the fourth. The x squared dx becomes a 1/6 du. But that's just a constant, and I can bring a constant out of my integral. So you'll see that I'll oftentimes just immediately, since there's oftentimes this little constant or fraction in front of my du, I quite often just immediately put that in front of the radical, the integral sign when I replace my u's. So now I have 1/6 u to the fifth over 5 plus c. And we can clean that up a little bit as we substitute back in our u, 2x cubed plus 5 to the fifth over 6 times 5 is 30 plus c. All right, let's try letter C. The integral of x times the square root of x squared plus 3 dx. I'm going to let u equal x squared plus 3, making du equal to 2x dx. So I'll solve for the x dx by making 1/2 du equals x dx. Don't automatically divide by this number. Sometimes you'll find that that number helps because it's in the problem. All right, I'll pull the 1/2 out in front, and I'll make this the square root of u, or u to the 1/2, du. Then we'll integrate. And plus c. Okay, so we'll now replace our u. Notice the 1/2 and the 2/3 will reduce to 1/3. And then this is x squared plus 3 to the 3/2 plus c. It's interesting to take the derivative of this. You'll notice that you would get, when you pull this exponent down, you would get 1/2 times x squared plus 3 to the 1/2 times 2x. And so the 2 from the 2x will cancel out that 1/2 that's left over. All right, let's take a look at the next one. I'm going to let u equal 3x squared plus 4. So then du is 6x dx, which I'll write as 1/6 du equals x dx. So this becomes the integral of 1/6. I'll pull it out. X dx is du, and then this is the square root of u. Rewriting gives me u to the negative 1/2 du. So our integral is 1/6 times u to the positive 1/2 times the reciprocal of 2, which I'll clean up just a little bit, is 1/3. I'll plug in my u, 3x squared plus 4 to the 1/2 power plus c. Really should have plus c as soon as I integrate. All right, I'm going to ask that you do these couple of practice problems, and then we'll go over them. All right, let's see how you did on these. You should have let u be this thing on the inside, x squared plus 2. So that makes du equal to 2x dx. Now, I'm trying to make it a 6x dx. So some people would just call this 1/2 du x dx. Then they have to pull out the 6 and the 1/2, and that becomes 3. But you can also just say 3 du, multiply both sides by 3, and get 6x dx. Just however you want to do it. By doing that, it might save half a step. I don't know, but you should get the same answer regardless. So this cube root becomes the cube root 1/3 of u, the 1/3 power of u. Then 6x dx becomes 3 du, so I'll just put du and a 3. Then we'll integrate. U to the 1/3 plus 1 is 4/3 times the reciprocal 3/4 plus c. So this becomes 9/4 times x squared plus 2 to the 4/3 plus c. All right, on this one here, I hope you let it be the thing on the bottom. So we'll let du equal 3x squared minus 2 dx. Now in this case, I'm going to multiply both sides by 2, giving me 2 du equals 6x squared minus 4 dx. Now I can say that 2 du replaces this entire thing on top, so I'll just bring out the 2. Then that's du over u squared. That's 2 times the integral of u to the negative 2 du. So that's 2 u to the negative 1 plus c. Or 2 times x cubed minus 2x plus 1 to the negative 1 power plus c. So, yeah, those were both a little bit tricky. Hopefully you did okay with them. Let's take a look at some more examples. All right, let's take a look at e to the 3x plus 1 dx. In this case, I'm going to let u equal 3x plus 1. And then I'll take a differential, which is just 3 dx. That makes this 1/3 du equals dx. So I bring the 1/3 out, and that just becomes e to the u du. The integral of e to the u is e to the u plus c. So then we'll replace the u with 3x plus 1 plus c. Now, when you do a simple thing, u substitution like that many, many times, hopefully you'll even do this in your head. Most professors in a college Calculus 2 class, according to the notes I see, usually would just do that in one step. So that'll make it easier for you to follow along. So just try and get really comfortable with doing that. Do it on paper for now and get to where you can see it. All right, let's try the next one. U equals negative x squared. Take the differential, you get du equals negative 2x dx. Now this one here, I can't really easily make it look like 5x dx, so I'm not going to try. I'll just make this a negative 1/2 du equals x dx. So this becomes negative 1/2 times the integral of 5. The x dx became the negative 1/2 du, so that's my du, and then I have e to the u. Now, if you want, you can go ahead and bring that 5 out while you're bringing out the negative 1/2. So it's really negative 5/2 times the integral of e to the u du, which ends up being the integral of e to the u is e to the u plus c. So this is a negative 5/2 times e to the negative x squared plus c. All right, let's try the next one. All right, I'm going to let u equal, what should it be? Well, I can either let u equal x squared, or I can let u equal 1 over x. And in this case, they both seem to be inside a function, but I think 1 over x is more to the inside, and I think 1 over x is going to have a derivative more likely to be what's on here. So let's do 1 over x. The differential then is du. This is x to the negative 1, so this becomes negative x to the negative 2, or negative 1 over x squared dx. So if I just pull that, divide both sides by negative 1, I get 1 over x squared dx equals negative du. So this becomes the integral. That's e to the u, and that 1 over x squared dx, all that's just a negative du. Then the integral becomes e to the u plus c, which I replace with e to the 1 over x plus c. I've been waiting for a time to bring this up. You may have been wondering why I don't put parentheses around it when I have something on the outside, like put parentheses here. It's just not necessary. Yes, that negative would actually be multiplied to both the EU and the plus C, but we don't know if C is positive or negative anyway, so it just becomes another constant. So it just traditionally or whatever, it's just not done. You just put the plus C outside of anything, okay? All right, let's take a look at the next one. I'm going to let u equal 2x minus 1. So then du is 2 dx. I'll just go ahead and divide both sides by 2. So I can pull out a 1/2. 1/2 du is my dx, so that's just a du. And this becomes u. When I integrate du over u, that's u prime over u. So that's just 1/2 the natural log of the absolute value of u plus c, which becomes 1/2 the natural log of the absolute value of 2x minus 1 plus c. All right, go ahead and try the next practice problems. Pause the video and give it a shot. All right, let's see how you did. Okay, on this one here, let's let u equal x cubed plus x. So then du equals 3x squared plus 1. Perfect. Dx, of course. That's a differential. So this entire numerator in the dx becomes my du, and the bottom is just u. The integral of du over u is the natural log of the absolute value of u plus c. Natural log, the absolute value then of x cubed plus x plus c. All right, now on this one over here, we could try and multiply this all out and then integrate it just from traditional ways. But it might be that this is actually the result of a chain rule. So if we let u equal x cubed minus 6x squared, if this works out to be some multiple of this, then we can use u-substitution. If we can't, we'd have to multiply them out. in this case, I get 3x squared minus 12x dx, which you'll notice is just this times 3. So if I divide both sides by 3, I get 1/3 du equals x squared minus 4x dx. So this whole thing here and the dx became 1/3 du. So I'll pull out the 1/3, and I'll call that u du, because that's just u. Integrate. I get 1/3 u squared plus c over 2. Because I raised the exponent 1, got to divide by the new one. So this becomes 1/6 of x cubed minus 6x squared plus c. So you can see where the u substitution wasn't absolutely necessary, but definitely made the problem less taxing. All right, let's try the next one. I'm going to let u equal x squared plus 4. So then du is equal to 2x dx. I'll divide both sides by 2, so I get 1/2 du equals x dx. So this becomes the integral of, well, pull the 1/2 out in front. X dx becomes your du, so this is just e to the u du. And the integral of e to the u is e to the u plus c. So replacing, we have 1/2 e to the x squared plus 4 plus c. All right, let's try the next one. The integral of e to the x over 1 plus e to the x dx. I'll let u equal what? The top or the bottom? Well, the bottom has a derivative of the top, but the top does not have a derivative of the bottom. So let's let it be let's let it be the 1 plus e to the x. Making a derivative just e to the x dx. So which is perfect for u substitution. So this is u du over u. And the integral of du over u is the natural log of the absolute value of u plus c. So this is the natural log of parentheses 1 plus e to the x plus c. So why did I remove the parentheses? Why did I replace the absolute value with parentheses? 1 plus e to the x can never equal 0, because e to the x is never negative or 0. So since it's always positive, I don't need the absolute value bars, and so we should remove them. That's a simplification. Or at least I could say we can remove them. Okay, the integral of cosine of 3x dx. This is the kind of thing you're going to see a lot. Again, I want you to get really quick at doing this. The u substitution is u equals 3x. So du is just 3 dx. So 1/3 du equals dx. So that makes it, after the substitution, this is just 1/3 cosine u du. So the integral is 1/3 sine u plus c. So 1/3 sine of 3x plus c. You can see how that 3x results in a 1/3 on the outside. All right, let's let u equal x cubed on this one. Don't let u be secant of x cubed, because secant squared is actually a formula that we have. So we like the secant squared. That makes du 3x squared dx. So 1/3 du is x squared dx. So this becomes the integral, with 1/3 on the outside, of secant squared u du, which is tangent u. And I'll go ahead and replace my u while I do it. Okay? All right, on this next one, this time, though, I do want to see this sine cubed. That is sine inside a cube. So let's let u be just the part that's cubed. That's the sine 5x, because sine 5x is cubed. And also note that the derivative of sine is located later in the problem, so it's a good choice for our u. Now, sometimes as you're doing this, you might accidentally pick the wrong u, and that's fine. If it just doesn't help, go back and choose a different one. Times 5, because of the chain rule. Derivative of sine 5x is cosine 5x times 5 dx. So I'll make this 1/5 du is cosine 5x dx. So 1/5 times the integral of u cubed du is all I have left. So 1/5 u to the 4th plus, u to the 4th over 4 plus c. And if I clean that up a little bit and replace the u is sine, so this becomes sine to the 4th of 5x over 5 times 4 is 20 plus c. All right, let's try the next one. I've got a cosine to the 4th, so let's let u be that thing that's inside the 4th power, which is cosine of x squared. The differential is du. Derivative of a co is negative, so negative sine x squared times 2x dx. If we look back at the original problem, we have an x dx and a sine x squared, so I just want to cancel out the negative and the 2, so I'll divide by a negative 2, giving me sine x squared times x dx, and I have each one of those things in here. So all that became negative 1/2 du. So I have u to the 4th du, because cosine x squared is my u. Integrating then gives me u to the 5th over 5 plus c. So this becomes a negative cosine to the 5th power of x squared over 10 plus c. All right, I got a few of those tricky ones for you to practice, so give that a shot. Pause the video and do that, please. All right, I want you to let u equal x cubed. So then du equals 3x squared dx. That makes 1/3 du equal to x squared dx. So this is 1/3 times the integral of sine u du. The integral of sine of u is negative cosine. So this is negative 1/3 cosine of u plus c. Negative 1/3 cosine, my u was x cubed. Replace that, plus c. All right, we'll try this one now. Let's let u equal cosine of 3x. So then du is a negative sine 3x times 3 dx. So I'll make that a negative 1/3 du is equal to sine of 3x dx, which is perfect. So this becomes the integral of u to the 4th. Sine 3x dx became 1/3 du, or negative 1/3 du. So we get negative 1/3 u, which is cosine. Oh, no, I'm not done integrating yet. I'm sorry. U to the 5th over 5 plus c. Now I'll simplify and plug in. U is cosine to the 5th power. Put it right there. 3x over 15 plus c. All right, let's take a look at the next one. Sine of x times e to the cosine of x. I'll let u equal cosine of x. So du is negative sine x dx, because we're taking derivative of a co. So it's a negative du equals sine x dx. All right, so this is e to the u, because u is cosine x. Sine x dx became a negative du, and I'll just pull the negative out in front. So this is negative e to the u plus c. When you integrate, negative e to the cosine x plus c. All right, on this one, we should let u equal e to the x. Which one? I guess it doesn't matter, but that's the one. So du equals e to the x dx, making this the integral of cosine u, and then e to the x dx is my du. The integral of cosine is sine u plus c. So this is the sine of e to the x plus c. All right. Now, you don't come across this all the time, but a few times you're going to see this. Sometimes there's some additional algebras required to make the u-substitution work. And you'll just get used to recognizing when this happens. So remember, when using a u-substitution, the resulting integral must not contain an x or dx. So let's take a look at how that works out in this first one here. They need a little bit more room. Let me spread this out. All right, so the thing on the inside is the 2x minus 1. So that would be our first bet, 2x minus 1. So then I take the du and I get 2 dx. Well, The problem there is that now, I could call that 1/2 du equals dx, but when I try and replace, let's see here, this is a u, so I have the square root of u, that's good, and then the dx is a 1/2 du, but what about this? I still got an x. What we need to do is actually take this and rewrite it. So make that u plus 1 equals 2x, and then that makes u plus 1 over 2. So just solve it for x. And so then this is 1/2 the integral of u plus 1 over 2 times square root of u, which I'll call u to the 1/2. And I'll do that, du. That's just a constant, so I'm going to pull that as well. It's on the bottom. See, that's over 2, so it comes out as over 2. 1 over 2 times 1 over 2 is 1 over 4. U plus 1 times u to the 1/2 du. Now, in this situation here, I need to distribute this u to the 1/2. That's the only way to make that work. U times u to the 1/2 is u to the 3/2. Then plus u to the 1/2 du. We'll integrate u to the 5/2 times 2/5 plus u to the 3/2 times 2/3 plus c. So 1/4 times 2/5. My u was 2x minus 1 plus 2/3 times 2x minus 1 to the 3/2 plus c. Oof, that was a long one. Oh, and I need one more parenthesis for that 1/4 on the outside. All right, let's try another example. This time I'm going to let u equal 3x minus 1. So notice this, what we call this extra algebraic substitution. Oftentimes when you have something inside something and then the same power, not the derivative on the outside, that's when you'll recognize you'll have to do this. So 1/3 du equals dx, but we're going to have to solve for x, so that becomes u plus 1 all over 3 equals x. Well, I think we're done with all this. Maybe I can just move it around here. Get you out of the way. There we go. Okay, so this becomes the integral of u plus 1 all over 3. And then the square root of 3x minus 1 is u to the 1/2. I'll just go ahead and put that on the bottom, okay, with the 3. And then the dx became 1/3 du, so I'll make it 1/3 here. I can bring out this 1/3, making this 1/9 times the integral of u plus 1 over u to the 1/2 du. And now, because this is just a monomial, earlier there's nothing I could do, but now I can actually divide by it. Making this u, that's u to the first, divided by u to the 1/2 is u to the 1/2. Subtract the exponents. Plus 1 over u to the 1/2 is u to the negative 1/2. We'll integrate u to the 3/2 times 2/3 plus u to the 1/2 times 2 plus c. So 1/9 times 2/3 times 3x minus 1 to the 3/2 plus 2 times 3x minus 1 to the 1/2 plus c. All right, you try this one. All right, let's see how you did. You should let u equal x plus 1. So du equals dx. Good enough. And x must equal u minus 1. So this becomes the integral of u minus 1 over the cube root of u, or u to the 1/3. And then simply dx became du. Because of that, I couldn't do anything with it first because I had this binomial inside a radical. But now I can actually divide. I get u to the, that's 3 over 3 minus 1 over 3 is 2/3. Minus u to the negative 1/3 du. We'll integrate and get u to the 5/3 times 3/5 minus u to the 2/3 times 3/2 plus c. So our final answer is 3/5 x plus 1 to the 5/3 minus 3/2 x plus 1 to the 2/3 plus c. Just a quick note, if you try and take the derivative of something like this to check your answer, it's going to be somewhat yucky. You would actually have to do some factoring out first to try and make it look right. That would be easier to factor out the like an x plus 1 to the 2/3 before you take a derivative. Just out of this front part, leave the constant off. That might make it a little bit easier. Otherwise, you're still going to have to do some factoring out then after you take a derivative. But you can make it look like this, but it is a little bit ugly. So you just kind of have to hope you did it right, usually. Or check with the calculator. Okay, that's it for this one. See you next time.